In this class, I'd like to refresh your mind about Mosfet. Yeah, that is the most important device on chip. So this chapter, we call it Basic MOS Device Physics. Actually, this is also from Professor Razavi's textbook, I think, maybe chapter 2 or something. Okay. Another. Oh yeah, this is from chapter 2 of Professor Razavi's analog CMOS design. Anyway, why we need to have such kind of very brief introduction? Yeah, if you would like to know everything in detail about the property of the device, how the device operates, actually that is some kind of solid-state circuit, solid-state device. So again, you need to focus on such kind of quantum physics, right? Or solid-state physics, yeah. But even through quantum physics, solid-state physics, I think it will take you at least one full semester to get full understanding. Usually it doesn't make any sense because the time is too long, and usually after that, most of the students are still confusing what's going on because solid states of quantum physics actually this is too hard to most of the engineers, too hard. A lot of theorems, a lot of theories we need to understand. So if we require that all the analog IC designers need to study solid-state physics first, then forget about it. I guess maybe more than, I cannot say 90%, but at least more than 50% of the engineers will simply turn their head away to study AI or to study the other topics. So this is correct in idea, all right? But in practice, it is simply too hard. All right, we can try to the other way, but if you can fully understand that, then it will be quite helpful to design your circuit because you get all the idea about semiconductor, about the semiconductor devices. It will be really helpful if you understand. But the problem is, it is very hard to understand through solid-state physics. And then we can go to the other side. We simply look at such kind of CMOS as a break box. We have equations, right? So you have, oh, this is the input, for example, VI, right? Then we get the other one, maybe VO or IO. Good enough. And what's inside? Forget about it. Okay, because again, according to EDA tools, they help us to have such kind of very detailed equations to help us simulate the behaviors of such kind of devices. Supposed to be. That is the easiest way. But it is only good for digital IC designers because they always don't need to fine-tune anything. But for us, we need to tune W, we need to tune L, right? We need to tune the bias. Unless you have much more understanding about the device property, you can make it in a very short time. So if you would like to fine-tune your circuit efficiently, actually the second is inefficient. So we have some kind of dilemma. In theory, the first is correct, but that is too hard. And then for the second, in practice, that is the simplest way. It's okay, but that is too simple, right? So what you can do is to help you have some kind of brief introduction as good as we can, and then, yeah, hopefully you can get something instead of nothing before you really design anything. So again, we do something in between. Yeah, in between the first and the second. Not so hard and also not so easy. All right? And I need to thank my lab mates, yeah, Professor Yang, Professor Song. This is in Dongjing University, and he's in National Taipei University of Technology. Anyway, some of the lecturers actually are from this one. If you would like, you can get online to download it. Hopefully, there is still something on the web. So this is our approach. From the very beginning, we will tell something about the structure of Mosfet. Because if you have no idea what the structure is, I don't think you can understand the operation principle. And then we will try to help you refresh your mind about IV curve of the Mosfet. If you apply some voltage, and how much current you can get, blah, 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 that is the definition for IV. Usually, according to fundamental circuit theory, we usually have this format, okay? Input here and output there, all right? So I over V means V, is the stimulus. You just have some kind of V as the input, then you get current as the output. So that is the definition for this. Okay? And then, to be a very good analog IC designer, you need to know the second order effect. For digital IC designer, forget about it. They even don't need to study this or even that. Forget about it. Usually they don't study anything related to device. The minimum I get, the bottom is logical gate, AND or NOT. But for AND or NOT, actually, you need a lot of MOSFETs, right? They don't touch anything. According to MOSFET, resistors, and for them, I don't think they have resistor, capacitor, no. Inductor, even too hard for them, all right? But as an analog IC designer, you need to know everything, okay? Not only the original property according to such kind of IV curve, but you need to know some of the side effects, the second order effect. For example, what is body effect? Channel length modulation, threshold, conduction, blah, blah, blah. And also we need to know and pay attention to such kind of parasitic, not only capacitor, but also resistor. And this is the reason why we need to know such kind of small signal model. But even as an analog IC designer, you only need to know the simplest one. I mean, the simplest small signal model. I will show you not the complete one, but much, much more complicated than you need to know. I would like to only show you that our spice does much more help, deliver much more help than you can imagine, okay? The model applied by our spice, iSpice, is much, much more complicated than what you learned from such kind of small signal model. Maybe at least one order or two, maybe one order or two order in complexity, okay? This is the general consideration. Why we need such kind of MOSFET? From the very beginning, any kind of transistor is supposed to be a switch. Okay? For example, BJT, right? Even earlier than MOSFET. What does it mean? It has only 3 terminals. And for the base, it is used to control the current flowing through C to E or E to C. It depends on you have NPN or PNP. Anyway, for NPN, the current will flow through from C to E. But how much? It is tightly controlled by phase. Okay, you can turn it on, you can turn it off, just like a switch. That's it. But again, for digital IC designer, they simply have only on and off. Yeah, they have black and white lifestyle. But for us, we are colorful. Yeah. So we have from 0 to 1, everything is possible. So you can turn it fully on, fully off, or anything in between. So for ours, we have 0 to 100% of conduction. But for them, only 0 and 100. Okay, nothing in between. Yeah, that is from the very beginning BJT. And if you focus on this Mosfet, yeah, metal oxide semiconductor field effect transistor. Wow. Okay, that's it. Mosfet. As a switch, again, it looks like this. The current flows from source to drain or drain to source. Again, depends on N-type MOSFET or P-type MOSFET. But how to turn it on, how to turn it off? You need to apply proper voltage to the gate. Okay? So, for NMOS, if you apply high, then it will be on. If you apply low to the gate, then it will be off. That is the simplest idea, but far less than enough. Yeah. So to get better understanding, this is for NMOS, all right? For PMOS, the polarity is reversed. So you need to apply 0 for on, 1 for off, right? And this is the reason why, okay, later for the symbol, we have a bubble for the gate of PMOS. Bubble means not. Inverted, that is what we mean in idea. Anyway, to get better understanding, yeah, we need to have such kind of MOSFET structure. All right? Yeah. This is again NMOS. And how about PMOS? Just think by yourself. All right? We don't have enough time to help you explain how NMOS operate and then go to PMOS. No, that is your own responsibility because their behaviors are similar to each other. All right. Only if you get good understanding about NMOS, I promise you, you can think PMOS by yourself. All right. So that is the structure, very important structure for NMOS. We have gate here. Okay. Usually, it is composed of polysilicon. Okay. Polycrystalline 多结晶. Yeah. Polysilicon, we call it 多晶系. That's it. But who is the main character? Actually, I need to warn you. All the equations you learned from microelectronics, they are not talking about gate. They are talking about source and drain. No. All the equations usually are for the main component, your channel. Okay? Again, please keep this in mind. All the equations you learn or you will learn only focus on channel itself. All right? It is the main component. For all the others, gate, source, and drain, body, they are only supporting characters. Okay? 他们都是配角，只有 channel 是主角。Yeah. So, how the channel help to conduct anything? Later we will explain. But from the structure, you need to know that for the source or the drain, they need to be highly doped. So you can see N plus and N plus. Why? Because we need to reduce the parasitic resistance. Okay? And then between the gate, yeah, the controller to control the current conduction on or off, yeah, in theory, and the main component channel. it needs to be isolated. Okay, how to isolate your gate from your channel? Oh, very simple. We have another layer here. See? Here, right? It is the so-called silicon dioxide. All right? That's it. Here. That is a very, very good insulator. And what is the channel or body itself? That is p-type, especially p minus. Okay, I mean lightly doped, very, very lightly doped. And later I will explain. The lighter, the better. Okay, yeah. So if you would like to compose, to fabricate such kind of MOS, it should be on the so-called P substrate. Okay, but can you fabricate your PMOS on P substrate? No. Why? Okay, the key issue is from the very beginning, you can see the channel and your source or drain, they are of different types. Here, the body, the channel is P-type. The source and drain are N-type, right? What does it mean? From the very beginning, there are two parasitic diodes. In last chapter, I help you to refresh your mind about diodes. So you have one parasitic diode look like this, right? And the other one look like that. What does it mean? The polarity actually are reversed to each other. So it means what? Never mind, you apply positive here, negative there, or reversely positive there, negative here. Because those two diodes, they are back to back. Okay, their polarities are reversed. So you don't have any way to turn the MOS on. So by nature, from the very beginning, the MOS needs to be off. And this is the definition for enhancement type MOSFET. You need to enhance the MOSFET, otherwise it doesn't conduct anything. It needs to be off. All right? But for what? Power saving. We need to save the power for the whole chip. So by nature, everything needs to be off, unless we would like them to on. Then we apply proper voltage to the gate to turn it on. That's it. On the contrary, we have the other type of MOSFET. We call it depletion type. Totally reversed in operation. Unless you deplete it. Otherwise, it is always on. Oh, that is really painful. Why? Everything after power, oh, they are conductive. If you say, no, I need to stop you, right? You need to apply some kind of very strong voltage to turn them off. All right? So for operation speed, depletion type is much better than enhancement type. But for power consumption, depletion type is too much. So usually we don't select the best. No. We select the least power. Okay? Anyway. So please keep this in mind. From the very beginning, if you don't apply any voltage to your gate, the MOSFET needs to be off, according to those two parasitic diodes. Diodes are very important to help MOSFET operate properly. Okay? And this is the reason why I need to help you reflect the idea about diodes. Okay. So it means what? If you would like to fabricate PMOS, it means the source and the drain needs to be highly doped as P+. But P+, P minus, P+. What does it mean? Yeah. No parasitic diode from the very beginning, right? It is shorted. Wow. So what type you have? Depletion type. Because from the very beginning, you have channel to conduct something from the source to the drain. it doesn't make any sense. Yeah, because it is really, really, how can I say, a power wasting. It will waste you a lot of power, so forget about it. And it means, yeah, if you would like to fabricate NMOS, yeah, good enough on P substrate. But how about PMOS? It needs to be on N substrate. But from the very beginning, you have only one type of substrate. That is the so-called wafer. For your wafer, you need to think. To dope the wafer to be P substrate, to be P type or N type, you have only one choice. Okay, so usually from the beginning, it is doped as P type. Then, how can you fabricate PMOS on P substrate? For humankind, we wait for decades, maybe 3 decades, 30 years to my memory from chapter 1. I have very brief introduction for you, right? To my memory, 30 years. Okay. Wow, for such kind of piece of cake, so easy idea, but humankind wasted 30 years. Why? Fabrication is not so easy as you think. Okay, that's it. All right. So the real structure, that is the real structure for mature CMOS process. You can see P substrate here, so you can have directly, you can fabricate NMOS. But how about PMOS? You need the help from the other layer. We call it NWell. That's it. Easy to test, right? But very hard to fabricate from the beginning for humankind. And it means 30 years to make it for humankind. Wow. All right? Okay. And also for fabrication, I mentioned in last semester, we have 2 kinds of fabrication for such kind of N+ or P+ for such kind of doping. Usually in the past we had diffusion, okay? But right now, most of them are doped by implantation. But anyway, never mind, you have diffusion of implantation. All the ions or atoms, they don't go directly, downward. I mean perpendicular to your wafer surface, then penetrate into the surface. Forget about it. Okay? Yeah, that is only in idea. But in practice, the atoms, the ions, actually they go not only down in this way, but also in that way. Wow, many kind of directions. And then you will get the so-called side diffusion here. Never mind by diffusion or implantation. Okay? Yeah. So we have very important parameters for such kind of MOSFET. First of all, how much current you can conduct? Because the carrier, the major carriers actually are all from source to drain. Okay? So the definition here, this is the width. How wide the interface? And drain your source, right? How wide our interface? The wider, the more current. I mean, under the same situation. So that is the definition for W, the width of your CMOS, of your MOSFET. Okay? And what is the definition for length? Here. Because how far from your side to my side? The longer, the worse. I mean for current conduction, right? Just like a resistor. So the length should be the distance between your source and drain. But usually for your layout, this is some kind of 3-dimensional view. But for layout, we only have 2D, right? So this is the gate, okay, and then that is the source and drain. This is source, that is drain, right? So only mouse is alive. The pen is dead. My finger is also dead. I have no idea. Okay, so what is the length by nature from here to there, right? Yeah, that is the length from layout view. That is length between your source and drain. But for such kind of three-dimensional view, because we have side diffusion here, right? Here. And side diffusion there, right? So the effective length actually is the length you draw during layout minus 2 ID. LD, sorry. LD means the amount of side diffusion. Okay? So this is the length, effective length here, and width there. We don't have such kind of side diffusion for the width. Why? Because this is the openings for doping. Okay? So side diffusion will go that way. See? To 4 directions. Okay? So it only affects your length here. How about your width? It's still from here to there, right? Configuration, that's it. So, how about the effective width? Oh, that is the width you draw without any WD. No. Okay? Keep this in mind. Oh, the other issue I need to remind you is from such kind of structure, the source and drain are changeable because they look exactly the same. I mean, according to the structure, they are exactly the same as each other, right? So it's up to you. It could be source here, drain there, but you say, oh, no. For my layout convenience, this can be drain, this can be source, that can be drain, as you like. I don't care. All right? Since they are swappable, it will help you to simplify your layout. That's it. But the other warning is for high voltage mode, forget about it. The source and drain are totally different in structure. So you cannot swap the source and drain for high voltage one. Okay? Only for regular Mosfet, not for any kind of high voltage ones. And how about the thickness of the silicon dioxide in the past? Yeah, tens of angstrom, but right now, maybe only 10 or even less. Wow. How much is such kind of angstrom? Actually, minus 10th order. Okay? If you have 10 angstrom, what does it mean? Wow, only 1 nanometer in thickness. 1 nanometer, it means what? A few layers of atom. Okay? Only a few layers. Wow. So it is quite weak in structure. For example, you have only 4 atoms in thickness. For the bonding, if there's anything wrong, you lose 1 atom. It means the robustness of the silicon dioxide will be reduced by 25%. Okay? Yeah. It is much easier to be penetrated by voltage ripple because everything is not perfect. Even for your VDD, even for your control signal to the gate, you don't expect, wow, a flat voltage. No, you have ripples, spikes. Okay, especially with RF device with very high frequency physical circuit, you have many kind of spikes. For such kind of spikes, it will be quite easy to penetrate the weak region of your silicon dioxide. Okay, so this is the reason why the thinner the silicon dioxide is, the less VDD you can apply. That's it. So from process evolution, for the better process, the thickness of the gas oxide will be reduced. and also the supply voltage. Otherwise, it is more likely for you to damage the device. Okay? That is a very simple idea for you to understand. Yeah, that is another view. Never mind, again, for MOS, the majority carrier actually is electron from the source. Okay? You can deploy a lot of majority carriers from source to drain. Depends on how much voltage you apply for your gate. And again, oh, this is polysilicon, right? Yeah, for the gate. And silicon dioxide in between your gate and your channel. Yeah. Sometimes, oh, okay. Sorry. From the very beginning, there is no channel for such kind of enhancement type MOSFET. After you enhance it, you can get the channel from 0 to 1. Oh, no. From nothing to something. Okay. So for such kind of substrate, usually we call it body. Okay. So we have 4 terminals for such kind of MOSFET. Your gate, your source, your drain, and your body. Don't forget your body. Okay, body is very important because body also has some kind of impact to the current conduction. Later, I will show you. That is so-called body effect. That is very, very important for analog IC designers. Yeah, never mind you like it or not. Even though you hate it, you still need to know. Okay. And how about digital IC designers? Oh, just forget about it. They can live happily since after. Yeah. Okay. That is the better view, complete view. On the same substrate, you can fabricate not only NMOS but also PMOS. Oh, since we need to apply proper voltages or current to all terminals, we have 4, right? So how can you apply proper voltage for your body? Body. Where is body? Body is here. Body means your channel in the future. No. After you apply proper voltage to the gate. Later I will explain how to create such kind of channel from nothing. Yeah, from the beginning you have only N plus, P minus, N plus. Okay, yeah, that is for P substrate, we call it body. How can you apply proper voltage to here, to the body, or to the future channel? From such kind of three-dimensional view, it is totally impossible, right? Okay, let's go further here. This is the idea, the key idea. Yeah, you cannot apply your voltage directly to the channel, to the body. So beside your main part, you have gate, your source, you have drain. Beside them, we have body contact. Okay, indirectly, you can apply the voltage here, then conduct to there. That's it. Okay, please also keep this in mind. There is no way to directly apply voltage. You can say, hey, from the very beginning, I can have a buried layer. It is possible. Then congratulations, you have some kind of deep layer, deep angle, deep any kind of layer to connect here to there, right? Only to please you, to make you happy. But it is not impossible, but it will be really expensive. Again, humankind always choose the device, the circuit, the process with least power consumption, with least cost. Okay, so if you would like to directly apply your voltage to your body, it is not impossible, but too expensive for humankind. So nobody would like to have such kind of very luxury, very expensive process. So what can we do to save money? No buried layer, no such kind of deep layer for you to connect your body voltage, body bias. Okay, so instead the body bias is applied again beside the main part of your Mosfet. But I need to point out that as close to your main body as possible. Okay? And then the other reminding is because the body here is P minus, right? So how can you connect your body to your P substrate? Through the help of P plus. Okay? This is a very important idea. Don't say, hey, look, this is N most. For source and drain, they will dope as N plus. Why? Because they need to have two parasitic diodes from the very beginning. So they need to be doped as N plus with different types. Okay? And how about your body contact? Hey, don't forget, the body contact is help you to conduct the voltage from here to there, right? Don't dope your body contact with N plus. Otherwise, you will have another diode. Who can help you? No, nobody can help you because for here and there, the parasitic diode can be erased, canceled by gate voltage. But we don't have another gate voltage to help you, right? So don't be silly. Here, you cannot dope it as N plus. No, only P plus can help you. So it means what? The terminal here will be connected to P plus and to P minus all the way to your body. And this is the reason why the doping for body terminal is reversed to your source and drain. Again, in N-well, you have PMOS. Yeah, the source and drain are doped with P plus. And how about your body? Again, no parasitic diode from the beginning, right? Right? So good. You need to dope as N plus for your body. Okay? Again, the body doping is totally different from the source and drain doping. That is the key for fabrication. And why? Why? I told you already. Because we need parasitic diode here, diode there, but no parasitic diode for our body contact. Keep this in mind. Yeah, and then we can go for because if for any circuit designer, you would like to design a circuit, you need to draw such kind of very complicated cross-sectional view. Oh, that is too hard. Okay, so to ease your life, we have symbols, much simplified version of the device. Yeah, for NMOS it looks like this. PMOS it looks like that. Okay, here the direction of your arrows. Yeah, that's it. This is for NMOS, that is for PMOS. So the arrows directions are reversed. Okay. Don't forget we have body, and we have a dash line. Why? No direct connection. For the others, they have solid lines, right? So they are directly connected. But this is not the case for body. Body is indirectly connected, as I explained already. We have even simplified symbols. NMOS and PMOS. What's the difference? Huh? Where is the body? There's no body. You must be careful. Unless you can connect your body to your source. I mean, you can short your body and your source. Otherwise, I strongly recommend you don't use such kind of symbols. As an analog IC designer, I strongly recommend you no. Okay? Because it's quite misleading, especially for new engineers. Wow, that is simple. Let's apply it. Because from the technology file from TSMC or UMC, they provide not only the complete version, but also the simplified version. For whom? Not you. For digital IC designers, not you. Okay, but ridiculously enough, almost all those digital designers, they pay no attention to this. Only us. Okay, we pay much attention, but this is quite misleading. Again, unless you can short your source and body, It means no body effect unless you can promise me. Otherwise, don't touch. Okay, I still recommend you, yeah, to work harder, to take a good care of 4 terminals instead of 3. No, usually you need to take a good care of all those 4 terminals. And then if you go for digital IC designer, they hate such kind of errors because they have no idea what does it mean. Okay, from N to P, from P to N, forget about it. So they can enjoy this. You can say NMOS and PMOS are exactly the same, right? Except for what? There is a bubble. Again, bubble means not. It means the polarity of the voltage applied to gate needs to be reversed. Again, high for on, low for off. But here, according to bubble, low for on, high for off. Okay? And then, this is the most important slide till now. How to make such kind of MOSFET, yeah, functional? Because from the very beginning, it is off. How to turn it on? How to make your MOSFET conduct something between the source and drain instead of nothing? From the very beginning, you need to take away the parasitic diodes. Okay? Let me see. Yeah, see? That is what I can help. From the very beginning, you have 2 parasitic diodes there. The polarities are reversed. So never mind. For example, you apply positive here, negative there. Oh, sorry for this one. The polarity is reversed. You say, hey, I changed my mind. Minus here, positive there, right? Oh, this one can be conduct, but that one is still reversed. No way for you to conduct anything in theory. So if you would like to conduct something instead of nothing, you need to get rid of those 2 parasitic diodes. But how? How to make them disappear? You can pray very hard to your God. Come, go away. Oh, you pray your God to make them go away? How many transistors you have? From the very beginning, I told you. Right now, yeah, in last year, not right now, we have 50 billions. Your God will be really busy only for 1 chip. Yeah, he needs to help you to turn on this, to get rid of that. That's too complicated. So you need to help yourself. How to get rid of them? How to make them disappear? Oh, simply by applying proper voltage to the gate. Okay? That's it. But how can you make it? Luckily enough, because the gate is conductive, right? And here, the substrate is also conductive. Semiconductor also, you dope something instead of nothing. Okay, the conductivity here is a little bit better than semiconductor because you have doped it. Anyhow, both layers, the top gate, the bottom substrate, actually both are conductive. In between, you have insulator. Oh, congratulations! What's that? What's that kind of structure? Capacitor. 2 conductive layers in between, 1 insulator. Good enough to be a capacitor. Okay? So, yeah, people always say MOSFET is a capacitive device. Why? If it doesn't have such kind of capacitance, I mean between the gate and your substrate or your channel, as you like, then it doesn't work. It heavily depends on such kind of capacitor operation. Otherwise, it is not functional. Okay? So between the gate, the insulator, very important, right? And the body, such kind of capacitor structure will help you because as the capacitor, we have Q equals CV. The capacitor means here, I mean the structure here. Okay, the capacitor. So usually we have C oxide. Later I will explain. Yeah. Anyway, Q equals CV. What does it mean? The more voltage you apply, the more charges will be stored into the capacitor, but to both sides, right? Not only one side, but two sides. Okay, bingo. So for MOS, if you apply positive voltage, you will have a lot of positive charges stored on the top. It means what? On the contrary, the same number of negative charges, electrons, free electrons, will be stored to the bottom. But from the very beginning, it is P substrate, right? It means what? You have a lot of holes, right? So the first mission is to store enough negative charges to kill each other, okay? Because from the very beginning, here is still P-type. To make it from P-type to nothing, bingo, to kill all the holes, okay? To make it type neutral. Oh, I am not talking about the charges, okay? I'm talking about in the beginning, from the beginning, you have a lot of holes there. They are positive majority carrier, right? To kill all of them, make no holes or electrons in theory, okay? How much you need to apply? How much voltage you need to apply to kill all of them, the holes in this region, all of them, to make it from P-type to no type? Don't tell me from P-type to N-type. No, that is our later story. You need to turn it from P-type to no type and then to N-type. Okay? So how much voltage you need to apply? We call it threshold voltage. VT or VTH as you like. Okay? Threshold voltage. That is the definition. To make the body, to make the substrate from P-type, I mean for MOS, from P-type to no type. Okay? Yeah, no type, what does it mean? It behaves just like pure semiconductor, intrinsic semiconductor without doping. That is what do I mean. Okay? But even in this way, you apply good enough threshold voltage to turn it from P-type to no type. Can it conduct something? Yes, but very, very little. To help you conduct, because right now, it is a pure semiconductor, right? For pure semiconductor, I told you already, how much is the conductivity? About -12th order of the conductor. Oh, that is really bad, okay? So please keep this in mind. From microelectronics, you learn, if you only apply VTH to the gate, the current should be 0, right? It is never be true. No, it is still conductive, but very, very less, very, very little. Okay, according to the conductivity of such kind of pure conductor is pure semiconductor, sorry, is really, really small. All right. So to conduct more current, meaningful current, the current here, maybe you can think, oh, that is leakage. No, dear, only leakage current. All right. To make it conduct some real current, meaningful current for you, you need to increase the gate voltage even further. Again, the more voltage means what? The more charges, positive charges here, negative charges there. But at this stage, we kill all the holes already, right? So the extra charge by applying even more voltage than threshold. Congratulations. Extra electrons will be stored in this region. to make the channel. Finally, we have channel. Here or there, no, we don't have any channel. So what does it mean? Unless you change this region from p-type to no type and then to n-type, then the channel will be formed, will be constructed. Okay? Oh, congratulations, because right now you have real channel, n-type channel. I mean, why it is n-type? Because it is composed of the majority carriers are electrons. And how about n plus? The same, n plus the same. Congratulations, since after they can live happily because all of them are n plus. A lot of electrons can help you conduct current. That's it. Okay? Piece of cake. That's it. Yeah. So, that is the formation of the so-called inversion layer. Why? Why we have inversion? Simply because from the beginning it's p-type. We make it from p-type to no type and then n-type. The polarity is reversed from p-type to n-type. So we call it inversion layer. More specifically, we call it strong inversion. Okay? Yeah. This is very important. What you learn from microelectronics, we call it saturation. Saturation region means what? For strong inversion. Okay? You have strong, right now we have strong inversion. It means what? We also have weak inversion. Okay, what does it mean? The operation is very close to this. You kill all the holes. Okay, and then very little electrons are stored here. So it conducts very little, I mean compared to strong inversion, weak inversion conduct very little current. But it still conduct current, okay, instead of no current, yeah. But what's the difference between strong inversion and weak inversion? In brief, again, strong inversion is what you learn from microelectronics for saturation. Okay, so later I will show you the equation. ID equals 1/2 mu COX double over blah blah blah. That is for strong inversion. Okay, and how about weak inversion? Oh, fantastic! Weak inversion. The IV equation look like this. Your voltage here, gate voltage. Okay, effective voltage. I mean subtract VTH, blah blah blah, and the current. Wow, the behavior is much similar to BJT. Again, in weak inversion, Mosfet behaves like very similar to BJT. What does it mean? According to the exponent here, you can get more transconductance. GM is much higher in weak inversion than in strong inversion. Okay, what does it mean? You can get much higher gain if you operate the most in weak inversion. All right? Wow. So why don't we go there? Simply because I told you the current in weak inversion is really small. So nothing is free. If you would like to operate your MOSFET in weak inversion, we call it subthreshold. Subthreshold, because we need threshold voltage to blah blah blah. So we call it subthreshold region, right? The good is very high gain. But what is the bad? What is the price you need to pay? Very low speed, because the current is very, very, very small. Again, speed and bandwidth, or the gain, right? They are contradictory to each other. If you would like to get higher gain, larger bandwidth, then the current will be real small, the speed, blah, blah, blah. Okay? Got it? So this is the operation for NMOS. And how about PMOS? The same. Okay? Anyway, from the very beginning, nothing. Okay, how to make it work? By applying good enough voltage to the gate from the beginning. VTH. See, you have P holes everywhere, right? By applying VTH, see, no carriers. Congratulations. Yeah, it becomes pure semiconductor, intrinsic semiconductor. After that, you can still to get more higher than VTH. Finally, you have one layer of inversion layer, strong inversion layer, to connect, because it is right now N plus. Okay, so you can conduct much current from source to journal, from drain to source. Yeah, that is the key idea. And then we go for threshold voltage. Threshold voltage is very important for Mosfet. Okay, for you, always, and even for me, because again, what is the saturation current? There is a term, VGS minus VTH squared, right? So it means what? To increase the total current, we hope threshold voltage can be as small as possible, right? To conduct more current. But how to make your threshold voltage as small as possible? Okay, according to steady state physics, quantum physics, I show you this. This according to the Fermi level. I mentioned in, and this is some kind of working function. Forget about it. Yeah, I would like to explain this. VTH actually is strongly dependent on C oxide. Okay, ox means oxide, silicon dioxide, the gate oxide between the gate and the channel. Okay, per area. That's it. Okay, yeah, I told you again and again, without capacitor, Mosfet cannot work. Right? So capacitor is the main principle for Mosfet to operate. Yeah, where is the capacitor? Again, the gate, the channel, and the gate oxide. So for such kind of parallel plate capacitor, 平板电容, you know this one. Oh, no. Okay, please go back. Yeah, what is the equation for parallel capacitor? C equals epsilon A by D, right? That is the area for top and bottom, the overlap area for the two conductive layers. And then D means what? The distance, right? So it means the thickness of your gate oxide. Because we would like to increase it, right? Why? Again, Q equals CV. From the beginning, you need to kill all the charges, all the holes here. Okay? Okay? So after fabrication, how many charges you have? That is fixed. The total number of charges in the channel area, the so-called channel area, is fixed. Okay? So, again, first of all, the higher doping for your substrate, it means what? The more charges here to be killed, right? It means the more threshold voltage, right? Right? So, I explain this for you. Q depression in the channel area, the more charges, the higher threshold voltage, right? Makes sense. It makes a lot of sense, right? So it means what? In the channel region, you need to reduce the charges. It means you need to lightly dope as lightly as possible. That is the difference between TSMC and UMC, blah, blah, blah. Okay? TSMC can make it lightly, even more lightly than UMC, than Global Foundry. So it can reduce, with the same, in the same process, 0.18, 19 nanometers. No worries. It can help you to reduce VTH. But how? This. Okay? And this is the reason why, never mind for NWL or for P substrate, it needs to be lightly doped instead of heavily doped. If you heavily dope this, then the threshold voltage will become sky high. It will hurt your operation speed. Okay? Got it? And then, again, the charges here are fixed after fabrication. What we can do? The charges here is fixed, but Q equals CV. The more capacitor, it means what? Because this is fixed. Okay? The more capacitance means what? The less voltage you need to apply. Bingo, that's it. All right? Right? So, the more C oxide, the less threshold voltage. That's it. I help you to explain the most important term in this equation. Okay? Even though, if you would like to derive the full equation, I promise you, really hard. After hours of studying or weeks of studying, most of you don't get the point. But within minutes, I help you to understand the most important one. Yeah. How to reduce threshold voltage? From the very beginning, the channel area needs to be lightly doped. And then, the effective capacitance needs to be increased. But how to increase it? Again, I told you, because, yeah, it is proportional to the area. And C oxide means per area. So you need to divide it by area, right? So no area. Okay? So C oxide will proportional to epsilon by distance. Yeah. So how to increase it? Two ways for TSMC or UMC. One way is to increase the epsilon, the dielectric constant, 介电系数, okay? Or to reduce the gate oxide thickness. Okay? If you learn already my analog IC layout, hopefully you can enjoy. Yeah, layout and design. Actually, they are related very much to each other. Okay? Yeah, blah, blah, blah. Okay, we can have a break here because I need to drink coffee. 10 more minutes for the break. And later when you come back, we can go further. Yeah. How to derive? I don't have time to help you derive it because that, again, for all those equations, if you are interested, please derive by yourself. Okay? I wouldn't like to waste your time. A lot of equations after tens of minutes of derivation, you get no point. It doesn't make any sense. My role is to help you explain. Okay? Through explanation, I hope you can fully understand the operation principle. By derivation, usually you will get nothing. Okay? Anyway, if you are still curious, the equation is correct or not, do it by yourself. That is your own responsibility, not mine. Okay? Again, I'm only a designer. I'm not any kind of physician or mathematician. Okay? So, logic thinking is the most important issue I can help, not for equations. Yeah. Unless you would like to publish some journal papers, you need to derive something. All right? Otherwise, forget about it. Okay, we can have a break right now. allow me to get my coffee.